pleasure to introduce Dylan. And so Dylan, I met, I guess, right at the very beginning of freshman year, and then I didn't see him again for a really long time. And then so I'm kind of like a gatekeeper. I saw him at the beginning, and now I have the pleasure to see him finish up. And so Dylan, come in a great time in the research. We're starting to look at sustainability, and we don't really have the lab infrastructure built up yet. So Dylan was very critical in helping us to start a new approach, a new field of research. So here's Dylan.
Hey guys, how's it going? I'm Dylan Brubaker. Dr. Paul's thank you for the excellent introduction. So I was working all semester on trying to build an absorption chiller prototype with the help of Dr. Paul's, of course, and the help of his lab and utilities. So absorption chillers, they're not new necessarily to us. They've been around since the 20s. Here we have an example of a Crossley ice ball chiller, which was developed in 1923. So it's not new technology. We're just trying to work on making it more efficient and bulking it up. So I'd like to start off with just going over, we're using an adsorbent and an adsorbate pair, and what the pair we chose. So like in this one they used ammonia and water for the ice ball. What we decided to use was we wanted to study activated carbon and methanol and how the adsorption works with those two pairs. So we can see here that activated carbon is extremely porous. It has an extremely high surface area. So basically, the way I like to put it into layman's terms is 1 gram of carbon has more surface area than an entire tennis court. So yeah, it's pretty mind-blowing because it's a tiny little particle, but it has these nooks and crannies that just make it extremely. And there's a schematic of it over here, so we can see molecules and ions and particles, and they flow into these nooks and crannies called mesopores or micropores, and they actually they bind to the surface of this activated carbon. So I just wanted to give you guys an idea of what the thermodynamics and the schematics of what my project looks like. And it's a pretty simple system, the way it's set up, but it's not easy to replicate. So we have an absorption chamber, which is the activated carbon, and then we have the coolant, which is the methanol. When we heat the carbon, the methanol returns back into the methanol chamber, and then similarly, when the carbon is cooled, it absorbs the methanol again. So we can actually get this cyclical or a cycle going. So when carbon heats, it desorbs. When it cools, it adsorbs. The cool thing about absorption chillers is they're low cost, or they can be, depending on what materials you were using. They've been around since the 20s, and the way they work is on the concept of evaporated cooling. So much like when we sweat, the sweat on our skin evaporates and it cools our skin. So it works on that concept. And it's based heavily, like I said, on the pairs chosen. So if we're using silica gel, or if we're using zeolite, or if in our case we're using activated carbon and methanol, and then also there's ammonia and water. What I was mostly focusing on was, like I said, I was mostly focused on activated carbon, and I needed to build a test bed to help characterize the system and to help me understand how it actually works. So I had 2 experiments basically. One of them was from a previous student's work, Danny Ryan. I'm going to get to that in a bit. He built a prototype for an absorption chiller. It hit some road bumps, and so I was trying to think of ways to get past those roadblocks. And then also we had to build a system that would study the thermodynamics of how an absorption chiller works. So this is a student Danny Ryan's prototype. It's a large copper tube that you would fill with methanol, and then we have a large copper reservoir that you would fill with water. And then when you attach a pump to the methanol chamber, it gets the pressure so low that the temperature gets extremely low, and it actually ends up producing ice, or it gets so cold that it can freeze water. And so imagine if we can fit 10 liters of water in there, or even more, we could freeze all that water and make it into ice, which would be very cool. So I did a couple trials. I did a dry trial with the copper tube. I filled it with methanol, put it on a roughing pump, a very heavy roughing pump. And I actually started to get ice, or I got frost on the outside of the tube after about 20 minutes of it pumping. So this is what the copper tube looked like after I had it on the large roughing pump. I tried multiple pumps. Some of them had better results than others. My best results were on the large roughing pump because it could get it to such extremely low pressures, and we want it at extremely low pressure because that's how we get extremely low temperatures. And then I also did a submerged trial where I submerged the tube into a graduated cylinder filled with water and began pumping it, and got so cold that I was actually able to produce ice. The only problem was I need a container that holds water where it won't cause swelling, because it can be kind of dangerous when you're working at pressures with water. And so you can kind of see here, well, I don't know if you can see it, but I started to form ice down here, but there was no ice forming. It wasn't uniform at all, so it started to swell. And if I kept running this experiment, I would have exploded the graduated cylinder, would have broken it. So there's some danger behind it, so we had to take that into account. But when I took it out, that's all the ice that I was actually able to produce. And this was on the large roughing pump too. The small roughing pump couldn't get it to low enough pressures, so we had to ramp it up a little bit. So this is the test system that I built. There's a lot going on in here, but if we go back, it's a lot more simple than it actually seems to be, because it's just like the first schematic that I showed you. So we have the adsorbent material, and then we have, the adsorbent material, we have, which is the carbon, we have the methanol in this bath over here, we have a condensing tube, and then we're monitoring the temperature of the methanol, because it uses evaporative cooling, so the temperature we should see a flux in temperature. And then we also have a pressure sensor attached to it, so that way we can measure the pressure of it. We have our heat source, which is a heat mantle. We have a second thermometer down here, which we could attach, and then the coolant, which is the methanol. What I was mostly trying to work on was investigating the principles of how this system would work and how I could get it to be more efficient. I was referred to an article where Wayne and Son were both able to produce 6 kilograms of ice using 500 milliliters of methanol. I'm not using 500 milliliters of methanol. I'm on a much smaller scale, so I'm just trying to replicate the results and see that this actually works and see that I can get the thermodynamics of the system to work. And then finding the carbon that will absorb the methanol, and it was a little difficult to find the right carbon on the budget that we had. I read articles where they used AC35, which seemed to produce the best results for activated carbon. That's what AC stands for, is activated carbon. And then I also took a look at which worked better, granulated activated carbon or powdered. Granulated worked better because when you powderize activated carbon, it takes away the structure, it takes away the pores, and we need the pores for the absorption. So we were mostly working with granulated. When I did an absorption run, I was really happy to see that. So I started off by, we have a heated carbon, and so then when we attach the carbon to the system, the temperature immediately starts to drop. This was over a span of 3 or 4 hours. So we see it drop, and it's steadily dropping until it reaches a certain point, and roughly about an hour, it reaches its minimum pressure, which was, I believe, 57 kilopascals. So when it started at about 100, so we actually got it to drop 40 kilopascals, which was really cool because it actually shows that it's absorbing the methanol. So we're doing something good. And then you see that after it absorbs all the methanol, it starts to go back up, and it starts to go back to equilibrium, and the pressure will start to rise. I had to cut it off eventually because this was, it could have ran all night. But you'll see after a while, it'll go back to 100 kilopascals and it'll level off. I ran into some pressure concerns when I tried to do the desorption run. So what I did was, so before I ended up heating the carbon, now I tried cooling the carbon to see if I could get the pressure to increase. And so one thing that was kind of funny was this jump right here, because as you can see in the last graph, there's no jump. So I didn't know what it was, and then advising with Dr. Pauls, he put it in a great way. So the pressure is increasing, and as the pressure increases, it actually popped my system apart. So it actually blew the top off my system, and then all that pressure that I just recorded just immediately drops back down to atmospheric pressure, which is 100 pascals. So yeah, that was not... so I built a test bed, like I said, using carbon and methanol just to study absorption. We wanted to measure pressure, temperature. We were using a thermometer to just see if the temperature would change, but I wasn't able to actually mount a temperature sensor onto my system. I ran out of time, because it would have been really nice to get a function of temperature over time. But one thing I did find out was in my research, making these prototypes, I was able to build a system that actually was able to replicate absorption and desorption, which was very key. And now I'm just hoping that someone next year will build off of my project and take the research that I've done and work on making it more efficient, scaling it up, making 6 kilograms of ice using 500 milliliters of methanol. I would just really like to thank Dr. Pauls again. Without you, I would have been so lost in this experiment, and your lab was a great help, and I'm just really grateful. So thank you for everything. Do you have any questions? Yeah.
What are some of like the large scale practical uses of this?
Well, one off the top of my head was that I thought was kind of cool was I was referred to another article where, so we have fishermen, for instance. So these local small time fishermen, they go out at sea and they catch a bunch of fish. How are they going to keep their fish from rotting? They actually put absorption chillers on their boats. They're not necessarily, they can be big and they can also be kind of compact. The ones that they use for industrial purposes are relatively big, but the cool thing is they were actually able to produce 18 to 20 kilograms of ice with about 20, or with a certain amount of methanol. But so we can actually, I can't remember the exact amount of methanol they used, but they were actually able to produce 20 kilograms of ice, which when we broke it down, I believe we realized that for every kilogram of methanol or of carbon that we had, we would be able to produce a kilogram of ice. So if they were using 20 kilograms of methanol or of activated carbon, then in theory they would be able to produce 20 kilograms. For me, I was working with 200 grams of carbon, so it was a much smaller scale, and so it was a little harder to replicate the results, but I still got some data that showed that what I was doing was actually working, and so that was really rewarding. Any questions?
Let's thank Dylan again.